4b, least squares regression line. So now we're going to talk about what I referred to previously as a trend line. That line that best estimates what the relationship is between the x values and the y values, or between our bivariate data. So with doing linear regression equations, we're basically going to come up with an equation for a line that's our best representation of the actual data and the relationship between them. As we saw when we were dealing with correlations, we saw that they didn't always match up perfectly. It's not like I can draw a line that goes through all of my data points unless I have a perfect positive or a perfect negative correlation. And most of the time we do not have that. So in this case, we will not have that. Now, what we're going to do here is we're actually going to address two different methods of finding the linear regression equation, or the least squares regression line. The first one is going to be based on the same method that we used for finding the correlation coefficient, so what I called the book method. But in this case, you'll find that if you know how to use your calculator properly, the book method is really easy. If you do not know how to use your calculator correctly, or you do not have a two-variable calculator, then this would be a bear. And I say that because, as you're going to see, the equations are not pretty at all whatsoever in any way, shape, or form. So here we go. So if you remember from your earlier days in mathematics, the equation for a line was y equals mx plus b. Well, we're going to use something very similar to that. We're going to say y hat is equal to b sub 0 plus b sub 1 x, mx plus b, okay? Where b sub 1 and this sub 0, sub 1, remember our s sub x, s sub y, it was just defining that's the sample standard deviation of the x values. That's the sample standard deviation of the y values. So these subscripts are just saying these are two different things. B sub 0, b sub 1, two different items, not the same b. B sub 1 is your slope. B sub 0 is your y-intercept. So you've got your slope and your intercept. And you remember y equals mx plus b was the slope-intercept form of a line. So we've got our slope and we've got our intercept. Now you may wonder why Mr. Davis keeps referring to this thing, y equals mx plus b, yet this is written as b sub 0 plus b sub 1 x. They wrote it in a different order. So you may be looking at, well, why? Why are they doing it like this? Well, because this is a general formula. This is a specific formula. This is the equation of a line. Y equals mx plus b. So they write it that way. Whereas this formula is expandable. Meaning that I could take this formula, and if it doesn't have a linear correlation, if it has a nonlinear correlation, I could add on to it and say plus b sub 2 x squared. Now I'm able to see it as a quadratic or a curve. Maybe it's not just a curve like that, so I can go plus b sub 3 x cubed. And now I add a little more of a double curve into it. Plus b sub 4 x 4 to the fourth. Plus b sub 5 x to the fifth, right? So I can keep adding on terms to this, getting into a higher and higher degree formulas or equations until I can do a really good estimation of the data itself. So that's the advantage of this formula being written this way. We do not need to deal with anything beyond linear, so that's why we keep it to y hat equal to b sub 0 plus b sub 1x. Now you may ask, what's with this y hat? Let me just make this much clearer that that is a pointed hat on there. Maybe you call it a dunce cap, I don't know. But y hat, when you see a hat on a variable like that, it says that that is an estimated value. So basically, when we come up with this formula, if we plug in a value for x, the independent variable, we can calculate what we would predict y to be. So what we would predict the result to be of this. Now, that doesn't mean that that's actually going to be the y value. That depends on how good of a correlation we have. If we have a perfect correlation, then yes, we use this formula and we're going to get y. If we have a less than perfect correlation, then it's going to be off by a little. If we have a weak correlation, it may be almost useless. If you have no correlation, it is useless. Okay? So we've got that formula there. And I'm just going to continue on with that formula and say, okay, so how do we find this intercept? How do we find the slope? Well, we find the slope, b1, by taking the correlation coefficient r and multiplying it by the sample standard deviation of y divided by the sample standard deviation of x. Now, if you remember, slope is rise over run, the change in y over the change in x. Standard deviation is just a measure of change. It's just the standard change. So we're taking the standard change in y and dividing by the standard change in x. That's just what we would normally call slope. But then we're multiplying it by the correlation coefficient. If the correlation coefficient is 1 or negative 1, then we're going to get that exact slope. It'll just be positive or negative. If the correlation coefficient is 0, then we're just going to have 0 as our slope of this, which means we're going to have a flat line, which means it's always going to predict the same thing. Anywhere in between for our correlation coefficient, and it's going to change how steep our slope is or how good of a predictor we have. So again, I love the way that this method shows what's really happening, and I also love the fact that if I know how to use my calculator to find the standard deviation of y and the standard deviation of x and the correlation coefficient, I just need those three values to find the slope. If I don't know how to use my calculator, that's where you remember what it took to get the correlation coefficient by hand, and especially what it took to get it by hand using what I referred to as the book method. It was that 5 or 7 columns of horrible calculations. So very useful if you know how to do it by hand. Sorry, if you know how to do it using your calculator, so you don't have to do it by hand. So that'll give us our slope, b1. Well, how do we find our intercept? Well, our intercept, b sub 0, is equal to, all we're going to do is we're going to rewrite this equation, solving it for b sub 0, which gives us y minus b1x. So y minus b sub 1x. Right, so I just solve for b sub 0. But there is something that we know, you will know and I know already, about any least squares linear regression line. And that is that it will pass through the point x bar, y bar, excuse me. The point x bar, y bar will be on any linear regression equation or any of these lines that we come up with. It will all exist because basically what a least squares regression line is, it's the average line through our data values. So that is the average point, so that point has to exist on it. If it exists on it, then we can use that in the slope to find our intercept. So that's our equation for finding the y-intercept. B sub 0 is equal to y bar minus b sub 1 x bar. So those are going to be our equations, and then we're just going to do just as it says here. We're going to say y hat is equal to b sub 0 plus b sub 1 x. And that's how we'll find our equation. All right, well, let's look at some data and an example and see what happens. And I'm going to cheat. I'm going to use data that we've already used. So we've got x and y. Technically, it's not cheating. It's just me choosing to use something we've seen before. So we have 11 and 20, 8 and 21, 16 and 12, 15 and 16, and 7 and 23. So what are we going to need? We're going to need R, our correlation coefficient. We're going to need our standard deviation of y, our standard deviation of x, our sample mean of x, and our sample mean of y. So again, we can use our calculator to do this. I would not use this method if I'm going to have to build the whole table to get this stuff. I would only use this method if I know how to get those values using a calculator. So when I do that, I come out with, and I'll just put them off to the side here. So I'll put down n is equal to 5 just so we have it there. We don't necessarily need it, but just so we have it there. N is equal to 5, x bar is equal to 11.4, and the standard deviation of x was 4.04. Y bar was equal to 18.4, and the standard deviation of y was about 4.39. So that's S of y, S of x, y bar, x bar. We need R. Well, if we look back, or if we plug it into a calculator, we see that R was approximately negative 0.9556. So that's what we came out to. And we see a good, strong negative correlation. So this should be a pretty good predictor of what's going to happen. So now we have those, we can just start filling in. I'm just going to switch colors so it stands out a little bit more. So B sub 1 is equal to R, negative 0.9556, times S sub y, the standard deviation y. Make sure you put the y on top. 4.39 over S sub x, 4.04. And when we plug that into our calculator, that comes out to be negative 1.04 approximately. I rounded to 2 decimal places. I didn't want to have to put all the decimal places in there that could happen, right? Just like I rounded these to 2 decimal places. So negative 1.04. So we have B sub 1. Oops, I forgot to put my 1 there. So we have B sub 1. B sub 0. Well, how do we get that? B sub 0 is equal to y bar, 18.4, minus B sub 1, negative 1.04, don't lose that negative sign, times x bar, 11.4. So B sub 0 is 18.4 minus a negative 1.4 times 11.4. Order of operations says multiply this together first, then do the subtraction. When we multiply this together, let me just grab that number quickly so we have it. So that's 1.04 times 11.4 gives us 11.856. So we have 18.4 minus negative 11.856 Remember, when you're subtracting signed numbers, you can keep change, gives us 18.4 plus a positive 11.856, which gives us approximately 30.26. So b sub 0, I'll put it over here, is equal to 30.26. So now we have b sub 0. We have b sub 0, we have b sub 1. We can get our linear regression equation. Y hat is equal to b sub 0, 30.26, plus b sub 1, so plus b sub 1 at negative 1.04 x. Now, I personally don't like to do it that way. If I've got a negative, I'd rather turn this into a minus. So I would personally do it as y hat is equal to 30.26 minus 1.04 x. But both of these are correct and both of those are equivalent. And that's our linear regression equation. Let's give it a shot and see what happens when we grab that calculator again and say, okay, well, what do I get? I'm just going to create another column up here. Y hat. And I'm going to plug these in. I'm going to plug 11 into this equation and see what I get for y. And see what happens. So, what does happen? Well, let's see. If I plug 11 in for y, 30.26 minus 1.04x, I get the following. Just going to get rid of that so it's not in the way. I get 18.82. If I plug in 8 for x, I get 21.94. 16, I get 13.62. For 15, I get 14.66. And for 7, I get 22.98. Now I know that's a little messy there, but if you look at that, that's actually not too bad. This one's off by a bit. Instead of 20, I got 18.82. Instead of 21, I got 21.94, so I'm within 1. Instead of 12, 13.62, that was off by a bit. Instead of 16, 14.66. Instead of 23, I got 22.98. Boy, that's almost dead on. But we can see that that's actually a pretty good predictor. Is it perfect? No. But remember, our correlation coefficient was negative 0.9556, so we didn't have a perfect correlation. We just had a very strong correlation. But that's one way that we can find the equation for the least squares regression line.